Consider this before viewing weather on Jupiter. What do you know about weather conditions on Jupiter? How do storms on Jupiter, such as the Great Red Spot, compare with storms on Earth? As you watch the program, consider the essential elements needed to create weather on any planet. Assignment Discovery now presents Weather on Jupiter.
Today's high on Saturn is minus 200 degrees Fahrenheit. Storm season is well underway as cloud cover increases.
Storm warning for Jupiter.
With further
50-mile-long
thunderstorms as winds in the Great Red Spot increase.
Red Spot increased to 400 miles per hour. Visibility on Io is dropping to zero. The radiation warning
forecast is at a maximum with other dense auroras.
65 of the summer dust storm on Mars. All regions of the planet affected. More bad weather on the way as this.
Alien weather, wild and extreme, rages through the solar system. But no one has ever experienced its fury until now. Storms from the planets are coming down to Earth. And all this alien weather is about to give up its secrets in a laboratory called Planet Earth. The outer solar system, realm of the giant gas planets, is the true home of the superstorm. The planet Jupiter is so vast that more than 1,000 Earths could fit easily inside, a planet that's all atmosphere. As long ago as the 17th century, the astronomer Cassini saw a mysterious dark shape moving on Jupiter's surface. The Great Red Spot turned out to be a type of hurricane, twice the size of the Earth. Now, after more than 300 years, the Great Red Spot is still raging, and it's not alone. The surface of Jupiter is teeming with storms. Weather on Earth is powered by the sun's heat, but Jupiter only gets a fraction of this energy because it is 5 times further from the sun than we are. Jupiter's weather is driven by a powerful engine deep in its secret interior. Flashes of lightning ever seen were detected on Jupiter by the Galileo spacecraft. Thunderbolts 50 miles across and 100 times brighter than typical lightning flashes on Earth. Only Jupiter's outer surface is visible, but its lightning gave us a window into the planet's hidden interior. And when 700 miles of cloud broke its surface, planetary scientists were seeing the same thunderstorms as those on Earth, but on a terrifying scale.
And this was extremely exciting because now we had lightning on another planet, and we've actually correlated the lightning with certain types of clouds that you see on Jupiter. In particular, these beautiful bright white plumes that come out of nowhere and just erupt in the low pressure regions on Jupiter.
Jupiter gives out twice as much energy as it receives from the sun, with heat left over from the planet's formation. As it cools, hot gases rise towards the surface, powering thunderstorms as they go. These are the thunderstorms on Earth, seen from space. Tim Dowling wants to know what Jupiter's thunderstorms look like from the inside, but he only has sparks of light to guide him.
Of course, when we do planetary science, we're always looking down, and when you're a terrestrial meteorologist, you get to look up where you actually get to fly through. we have a lot of limitations. We have this great existence of lightning. We know some other things about it, but we can't get inside the thunderstorm on Jupiter.
Tim is a professor at the University of Louisville. For the past 5 years, he's been analyzing data from the only spacecraft to attempt the perilous descent through Jupiter's atmosphere.
3, 2, 1. We have ignition and liftoff of Atlantis and the Galileo spacecraft bound for Jupiter.
In 1989, Galileo was launched on a mission to study Jupiter and its moons. After a 6-year odyssey, it was in a position to drop a probe through Jupiter's clouds.
We were able, because it was an orbiter instead of a flyby mission, to plan very carefully a sequence of experiments or observations where we could look for lightning, and we knew pretty much where to look. We want to look in the low pressure rather than high pressure, in the low pressure zones on Jupiter.
Low pressure means thunderstorms, and the probe went in at 106,000 miles an hour. The probe headed for the center of the planet. It fell for 57 minutes, but to Tim Dowling's dismay, it detected almost no water. And with no water, there was no sign of thunderstorms. By sheer bad luck, it had hit one of the driest regions on the planet. 97 miles down, radio contact with Galileo was lost, and the probe was gone forever.
Just one sample of this enormous planet, it's tantalizing, but it raises more questions than it answers.
Tim hadn't found his thunderstorms on Jupiter, so his quest to understand them shifted to the Earth.
We're here inside the atmosphere of Earth, of course, and looking up. So you can get a great deal of information about the storms, the mechanisms for thunderstorms and lightning by doing very careful measurements of Earth's atmosphere and then try to carry that over to Jupiter.
Those measurements are about to be made. At the height of the summer storm season, over 100 weather scientists have converged on the Kansas prairies for the biggest study of thunderstorms ever held. They're hunting for supercells, the most dangerous thunderstorms on Earth. Planetary scientists like Tim Dowling believe that giant versions of these storms are producing the lightning flashes beneath Jupiter's surface. The hot afternoon sun is evaporating moisture from the land, creating tall columns of rising cloud. Thunderstorms in the making.
Down the Cheyenne Wells. And I'm sort of thinking that you guys might want to head down that way.
The Earth experts want to understand how storms build. In order to predict them, they need a three-dimensional portrait of a storm. But they have to catch one first, and they have a Jupiter expert on their tail.
They've got storms here, 10 o'clock, 2 o'clock, all the way across the horizon, and they're going to have to make some choices. It's going to be really cool to see how they decide where to go to put the first balloon up.
Command Post radar shows that one of the storms they're tracking could become a supercell. Ground teams race to head off the moving target, and Command brings out its secret weapon. The heavily armored T-28 military aircraft is scrambled to fly directly into the heart of the storm. Its mission is to measure the strength of lightning inside the supercell, something that can only be done from the air. It sounds like madness, but this is the only aircraft in the world that's licensed to do it. Tim Dowling hopes that by establishing a relationship between lightning intensity and the size and growth rate of the Kansas storm, he'll be able to do the same for Jupiter.
What we need is a fairly robust or very good model of lightning and thunder. If you have a model that does a good job of predicting or describing Earth's weather and Jupiter's weather at the same time, then you feel much more confident about the underlying physics and your understanding.
Ground forces launch a balloon into the storm to measure how fast and how high the thundercloud is rising. Above them, the T-28 approaches the most dangerous part of its mission. The massive updrafts of the storm threaten to tear the plane's wings off in a process known as wind shear. The same forces create lightning when water droplets freeze into ice particles at high altitudes. As they rise inside the storm cloud, they rub against each other, creating massive charges of static electricity. Eventually, enough charge builds up to explode as lightning.
And it's getting pretty dark. I don't know what's coming next. And lightning. Very close. Lightning, lightning. Lightning, lightning.
The thunderstorm is now 10 miles high, the maximum possible before it hits turbulence in the atmosphere and flattens out. This is an enormous storm. Suddenly, a tornado touches down on the horizon, the supercell's frightening calling card. The second balloon launch has to be fast. Just a few miles away, the twister is already causing havoc. The T-28 has detected so-called super bolts in today's storm. On hot summer days, the atmosphere expands, and thunderstorms can climb much higher than normal. This one went to a height of 10 miles, with updrafts of 100 miles an hour. Tim Dowling has seen that the more room a thunderstorm has, and the faster it grows, the bigger the lightning it produces. And in his imagination, he descends into the colossal thunderstorms to the west of the Great Red Spot.
See this incredible eruption, almost an atom bomb that's going off. And it's the size of Alaska, this thing. So it's just going to be like a wall, an enormous wall that goes up. And instead of going up 10 miles or so, we're talking 30 miles and just towering up overhead.
Now Tim wants to compare Jupiter's lightning with Earth's. No one knows lightning like a T-28 pilot.
This thing can get hit by lightning.
Yes, in fact, we've...
Charlie Summers shows him the damage.
Lightning strikes that have hit the aircraft.
What does that look like? Can we see?
Yeah, let's take a look back here. Usually the lightning, when it strikes the aircraft, doesn't leave any damage, but usually we get an exit. Like,
oh, interesting.
This is an exit where the lightning actually came out. Now, it's not that even when it happens, but I usually smooth them out a little bit just...
So that's like a thumb's width, that's a typical size?
Yeah, and that's a pretty heavy lightning bolt that is burned as it comes out. And the aircraft's been hit...
Oh yeah, there's chips all down here.
Yeah, and then there's bigger...
These nightmare thunderstorms are small fry, providing energy for something far more terrifying. Energy to feed a storm twice the size of the Earth. Energy that's kept it churning for more than 300 years. Energy that powers the Great Red Spot. Jupiter's Great Red Spot may have been around since long before the dawn of astronomy, and it looks like it will exist forever. But how can it live so long when the biggest storms on Earth last for only a few days? At the University of Washington in Seattle, Professor of Atmospheric Sciences Peter Rines thinks the answer lies in a bowl of water. A model of Jupiter's atmosphere, where he will attempt to create a great red spot.
Okay, take it up. Okay. Going to Jupiter, going to the outer planets, you've got gas atmospheres. They're doing almost the same things as a bowl of water spinning on this table. So we can actually build a planet or half a planet right here in the lab.
The first step is to get the right shape, a hemisphere, or half a planet.
Okay, let's go up to 3.4. Okay. See if we can make it more like Jupiter.
Jupiter spins 2.5 times faster than the Earth.
One of the remarkable things about this new substance you make when you take ordinary gases, ordinary waters, and spin them, is that they start organizing. And I think we've grown up in a world where moving your hand through a fluid makes just incredible chaos and complexity and little whirlies that you can't understand. If you go to this rotating world, this spinning fast world, you'll find that it's organized. There's order coming out of chaos.
The dye forms rings in the water, just like the rings around the planet. But they need to disturb it to try to make storms. Peter thought about why storms might exist in the first place, and realized that Jupiter and the Earth have much in common. On Earth, the biggest storms we have are hurricanes, our closest equivalents to the Great Red Spot. A hurricane sucks up its energy from the warm ocean, enough to power winds of 150 miles an hour. But Peter thinks the biggest clue is that hurricanes always move from warmer to cooler areas of the Earth. He believes that storms on both Jupiter and Earth are doing exactly the same job: air conditioning the planets, regulating their temperature.
When you go to a fully featured planet, there has to be a source of energy, a fuel for all the motions you see. That fuel is heat. It's the heat of the sun, or it's the heat boiling up out of the core of the planet. What the storms do, they take the heat out of the hot zones to the cold regions. It's an air conditioning system, a gas conditioning system, which carries heat out of the tropics of the Earth or of Jupiter to the poles and then sends it out to space. In goes the North Pole.
The model is missing something. It needs a polar region made of crushed ice to create the temperature difference that Jupiter has and that its storms need.
It's actually doing very well.
Suddenly, Peter's planet is teeming with storms, just like the surface of Jupiter. All the storms look very stable, but they can't all last forever. There is only one great red spot on Jupiter. Then Peter realized something amazing is happening. The storms are eating each other.
In a rapidly rotating planet like Jupiter, the eddies can't move north or south. They have to jostle each other like ball bearings in a raceway. They can increase their lifetime, grow older, last longer. They've lasted hundreds of years by competing with each other and actually gobbling each other up. The engine is turned up faster, and they compete for space, and one of them wins. And it lasts almost forever. And that's your great red spot.
The Great Red Spot is the solar system's greatest predator, a storm that eats hurricanes. It dominates Jupiter like no single storm has ever done on Earth, or any other planet we know of. Everything about it is extreme. A single storm big enough to swallow the Earth whole. A storm raging unchecked for over 300 years. But a storm that obeys the same laws as our own weather.
Jupiter is, in some ways, a simple model of Earth. I think ever since we had the really close encounters with Voyager flybys, and we had these stunning images of the red spot, the simplicity of it is wonderful and beautiful, and that many of us think that that's a piece of the Earth's action laid out before us.
By studying how this simple storm moves heat around Jupiter, we may learn how to predict the path of hurricanes on Earth, because the Great Red Spot is the most predictable storm there is, a monster that devours everything in its path. Only one thing can be predicted about hurricanes on Earth. Even the worst always run out of energy. In 1998, Hurricane Mitch struck Central America, the most devastating hurricane this century. By the time it blew itself out, it had devastated 6 countries, claiming the lives of 11,000 people and making 3 million homeless. Mitch found a way to be continually refueled. For almost a week, it came as close as possible to being the Earth's Great Red Spot. Having built up to Category 5, the most violent form of hurricane on Earth, it ran into the mountains of Honduras and stalled. With most of its body over the warm ocean, it sucked in heat for days on end. After being battered by 180-mile-an-hour winds, this region suffered 25 inches of rain in just 6 hours. A deluge that washed away entire towns. But when Mitch drifted further overland, far from its source of life, the warm ocean, the storm itself began to die. Sooner or later, even our biggest hurricanes will hit dry land and run out of energy. But on the giant gas planets, storms are far more stable and more severe. Even at its worst, our weather will never wipe us from the face of the Earth. The Earth will never become Planet Storm. But if we journey to the planets, alien weather is lying in wait. And it's an awesome reminder that there is truly no place like home.
Keep watching. Discussion topics and activity and resources for weather on Jupiter are up next on Assignment Discovery. Now that you've seen weather on Jupiter, talk about this. Jupiter's Great Red Spot has existed for centuries. How do scientists on Earth simulate Jupiter's superstorms? What have they discovered about the storm's longevity? Why are storms on Earth more limited in size, power, and duration? Now try this. Illustrate how a thunderstorm develops. Draw the path of water droplets from evaporation to cloud formation. Show how updrafts move charged water droplets within clouds, resulting in lightning. Log on to discoveryschool.com for curriculum materials and resources to support weather on Jupiter. To learn more, Assignment Discovery suggests Jupiter by Gregory L. Vaught.
The preceding program is part of Cable in the Classroom, a free service of the cable communications industry and your local cable company.